Hello and welcome to Disseminate, the Computer Science Research Podcast. I'm your host, Jack Wardby. Today, I'm delighted to say I'm joined by Semih Salihoğlu, who will be talking about a new graph database management system, Kùzu. Semih is an Associate Professor at the University of Waterloo and is also the current holder of the David R. Sheraton Faculty Fellowship. Welcome to the show, Semih.
Thank you very much. Thanks for having me.
Great stuff. Well, let's jump straight in then. So maybe you can tell us a little bit more about yourself and how you became interested in researching databases. Yeah, and your story so far.
I see. Good. Well, okay. So you should interrupt me because I could go on long here. So I got introduced to data management back in undergrad when I took the introduction course, and it was given by I went to Yale as an undergrad, and it was given by Avi Silberschatz. So Avi is very well known in the field, and he is actually the author of one of the main books. Well, the course was overall, I thought, very boring. Actually, we have a problem as a field to teach that course in an interesting way. I find it very challenging to myself to engage students because a lot of people know of SQL and sort of core database technology. But Avi had a way of explaining a lot of stories because he was very well integrated with the industry. So he had led the AT&T labs for a long time, and he had very close connections at Google. So he would inspire us a lot with these major challenges in data management. So that's where it started. But I did my senior thesis in networks. I was always a bit systems oriented, maybe a bit more theoretical bent, but picking topics from systems. Anyway, so I did have a 3 years industry experience before starting my PhD. And when I applied to PhD, I applied broadly as systems, not necessarily just data management. So it was networks or data management. And when I went there, I had a few sort of rotations with people, and believe it or not, I ended up in a very, very different field. I ended up in DNA computing, nothing to do with systems, nothing to do with data management whatsoever. But that lasted for about a year and a half, and towards the end of my second year, I came back to where I felt more comfortable, aligned with Jennifer Widom, who was my PhD advisor, and yeah, so that's how I sort of ended up doing a PhD in graph analytics, not really data management. It was the Hadoop MapReduce era, and systems like Spark were coming out, and everybody was trying to do some distributed sort of data management, data processing. And I picked the graph vertical because I just read this Pregel paper back in the day. We could get into that if you're interested. And then, so that was basically my PhD. And then when I took my position at University of Waterloo, I wanted to do something a bit more in data management. And there was a way around property graph data management with Neo4j. And yeah, I wanted to get into the space, and that's what I've been doing for the last 7-8 years.
Yeah, and the rest is history, I guess. Yeah.
Yeah, the rest is history.
Fantastic. So yeah, graph databases then. So that's what we're going to be talking about today. So maybe before we start talking about Kùzu, maybe we could, for the uninitiated, maybe you could tell us a little bit more about graph databases, the background, kind of what they are, what they're used for, and how they differ from relational databases.
Yeah. So I'll actually unashamedly put a plug for a blog post that I wrote that really articulates my opinions in this field in more detail than I'll probably be able to do right now because of time limits. But there's a blog post that I wrote on Kùzu's website called "What Every Competent Graph Database Management System Should Do," where I also go into the history of graph database management systems. So graph database management systems, the term might mean several different things. So nowadays, a lot of the time, people just think of systems like Neo4j because that's essentially the current most popular model is what's called property graph database model, and Neo4j really kind of pioneered that and popularized this. But systems based on graph structured data as a data modeling choice, graphs have been existed even before relational systems. So the very first database management system in history was based on a data model called the network model. A network is just another term for a graph. So it was essentially a way you would represent your records, and you would link them to each other, just like you link nodes through each other in the current property graph database management. So that's even in early 60s, before as the field was emerging, there were systems we could call graph database management systems. So And every wave has essentially seen to different, levels of success. Some database management systems that have been adopting a graph-based model instead of the at this point the de facto tabular model, or we could refer to them as relational model. So that came in the 60s. The first systems in relational systems were built in the 80s, and again 80s, 90s, 2000s. There was always database management systems built on a graph model, like XML, RDF, now property graph database management, object-oriented systems. So what should I say about them in the current era? So graph database management systems, they adopt a graph model where instead of representing your records as a set of tables, you represent them as a set of nodes and connections or relationships between your set of nodes. And in the property graph data model, you can also add some properties, key value properties on your nodes and edges. Ultimately, the query language it's a high-level query language, just like SQL, and it's very much like SQL. So Cypher is the one that Kùzu implements. Neo4j, it's Neo4j's language. We try to follow the open Cypher, but other systems too around that adopt the property graph model, they have high-level languages that are very much SQL-like, and it's not very surprising because that's in the end the core principles of how data is managed at a sort of database management system that is always relational, in the sense that there's only one way that humans know how to develop declarative languages, and that's really to compile them down to relational operators that process sets of tuples, output sets of tuples. So at their core, just like any other database management system ever built in history, they're all in a sense relational at that sense. But the data model in the query language has these graph-specific syntax or graph-specific features, which makes it suitable for several classes of applications, in particular, so like fraud and recommendations. Whenever you want to do essentially some recursive computations, I think they're much better than relational systems to program, because they have these special syntax where you can say, I want to find connections between this record and that record, and you may have represent them as nodes. And that's very intuitive in a graph model. You're essentially looking for paths. So paths is, for example, a very first-class citizen notion, which doesn't exist in tables, and you need to think of joint paths and whatnot, which is not very intuitive. So there's a mismatch there. So there's other classes, sets of features that they provide, and I go into all of these in my blog post. And but overall, essentially, the two things to really remember is that it's an alternative data model with a SQL-like language with alternative syntax. And I actually think people should just know alternatives to data management beyond SQL, just because there's never going to be a perfect fit database management system, and every system, every application has its more natural way of modeling it and asking queries, and different systems are going to be more suitable.
On that then, so Kùzu, give us the elevator pitch for Kùzu, and maybe tell us where the name comes from as well.
So Kùzu, the elevator pitch for Kùzu is aims to be the DuckDB for graphs. And not right now, for a lot of people, that means something very specific, because DuckDB is very, very popular and successful system. It is a modern graph database management system built with state-of-the-art principles of how essentially general analytics oriented or query oriented, I should say, database management systems should be built. And it follows the usability features of DuckDB. It's embeddable just like DuckDB, and aims to connect very well with sort of a set of higher level analytics libraries, specifically graph analytics libraries that users might use, aside from the database engine. So one way to think about this is that we'd like to be default storage of database management storage for people who would like to model their data as a set of node and relationship records, but they'll do maybe some high level, more advanced analytics, like maybe they'll want to build a graph machine learning model over those records, and they'll need to do lots of things before they could essentially tailor their records into the format that these higher libraries want. And we'd like to essentially facilitate that. Aside from that, for the classic applications of graph database management systems, so if you just need the graph database management system for your application, we want to offer a lot of value by being a state-of-the-art system, in the sense that we've done a lot of work on graph database management systems and query processing and scalability in particular. So all of those features are getting integrated into Kùzu. So, and that's also what DuckDB does. DuckDB also for the tabular analytics integrates state-of-the-art techniques, plus integrates very well with these higher level, the tabular analytics libraries like NumPy, etc. And we're kind of trying to replicate that.
Awesome. So let's go into the architecture a little bit more of Kùzu. So you said it tries to bring in all of these state-of-the-art components and the latest research into the system. So maybe you can tell us like the high-level picture of it, and maybe we'll walk through it component at a time. Then.
Sounds good.
Yeah.
So it's the high-level sort of principles of how database management systems are implemented is very well known. Like every system pretty much goes through similar sets of phases when they take a text query and in the end execute the query with some executable code. So basically we have a parser, binder, etc. to compile the text query into some in-memory representation. We have an initial join optimizer that actually, we're a little different from some systems that our initial join optimizer takes the initial representation of the query and optimizes and gives the logical plan that optimizes the joins that will happen in the query. And then we have an optimizer that takes that logical plan and does a lot of standard optimization techniques like filter pushdowns, removing of projections, removing of unnecessary properties / columns in relational terms, several normalizations, so on and so forth. And then that's mapped into a physical plan, and then physical plan is given to a task scheduler which executes it. So that's the high level sort of journey as it's the journey in Postgres, as it's the journey in, I'm sure, Neo4j or DuckDB. So that high level thing is pretty standard. So I should maybe just start talking about the query processor, because that's where we have done most work. So Kùzu is essentially the successor of a previous system called GraphFlowDB. So GraphFlow started in 2017, and the motivation for GraphFlow was, and when I entered essentially this field of graph database management system, I had felt that back in my PhD, I'd made a big mistake by not understanding how the software that I was using was, that I was spending my years on doing a PhD, was used. So I worked on these distributed MapReduce-like systems called Pregel was the original system from Google. The version that I have was called GPS, and the open source clone of Pregel was something called Apache Giraffe. It's still out there, I think, but I doubt it has any users. So I did my PhD on that, but I'd never really sort of understood the user base and understood how big, how impactful work in that space could be. So in general, if you want your research to be impactful, you need to bet that the software that you're working on, at least in data management, at least we all work on some data management or some data processing software, you need to bet that that's going to be successful, that that's going to live, there will be lots of applications using it, it will be popular to some extent. And I'd not done any of that work. I just blindly went into it, and by the time I was graduating, it had become clear to me that really there were no users of Giraffe or Pregel or GPS, those kinds of systems. I didn't want to make that mistake. At the same time, in 2015-16, Mike Stonebreaker won the Turing Award and had this Turing lecture where he talked about the importance of sort of talking to users throughout his career. Obviously he represents one style of research where he advocates that the true validator of good and bad ideas is the market, not reviews or academics. And so I did this user survey. I was able to convince my PhD student Siddhartha to really lead this. It was actually a lot of boring work to try to do. If you're a systems-oriented student and you come into my group and I get you to work 9 months on a survey, it's super boring. But I mean, he went through it, thankfully. Instead of coding, we did this user survey where we asked 90 people. It was an online survey. There were 90 sort of participants in the online, so 89, I think, participants in the online survey. Plus, I think we talked to maybe 15 users to really understand what their challenges were. And I think a lot of the people were actually coming from Neo4j, or other graph database management systems, although we wanted to do the survey a bit more broader by talking to users of Giraffe and NetworkX and other sort of popular graph libraries as well. But I think many of the people were essentially coming from Neo4j because it had the biggest user base. And we asked them, what are your problems? And they really told us scalability is a big problem in the field. So that's how we positioned our research back in the day, around 2017. Let's work on scalability, how to make essentially graph querying more scalable, graph storage more scalable. Amin really led the project. Amin Medvi is one of my PhD students who's graduating this year. He was the main essentially researcher on the system. And, so a lot of those ideas actually are now getting into Kùzu, and a lot of that work was either in storage or query processing. So maybe in terms of those two, we have the most sort of we have integrated most of the state-of-the-art techniques that we know. So what are those? So in the query processor, Kùzu is a factorized query processor, which means that the intermediate results are represented not as flat tuples, but as unions of Cartesian products. And I can get into this. It implements some of these novel techniques, join techniques for many-to-many joins, for growing joins, which is a core problem in graph querying. And it then integrates these very well-known and adapted, very well-understood techniques like it's vectorized in the sense that columnar DBMS relational systems use the term. So it means that instead of passing single tuple between operators in your query plans, we pass 2048 tuples are being passed, and that's the term vectorization in the context of query processing. So it's a vectorized query processor, and it does morsel-driven parallelism, which is a technique that came, I think, maybe introduced in Hyper, I'm not sure, but it was a Thomas Neumann paper. And DuckDB adopts it too, we adopt it. It's a way of parallelizing a single query plan instead of parallelizing multiple queries running in parallel. So basically, it's a very simple idea. It just means that if there is a pipeline, suppose you need to scan and filter something, right? So let's take something very simple. You need to find all your nodes that have an age greater than 50. And there's maybe, 1 million nodes. Morselization just means that you partition the amount of data from disk that needs to be scanned, and different threads are competing to get different morsels, essentially partitions of things, and they run different pipelines and they coordinate at where the pipelines end. So that's the way we parallelize queries. So those are essentially maybe the core sort of ingredients to the query processor. Storage it's a columnar design, but it's graph optimized. So why is it columnar? The motivation for this, and this is essentially our position as a research group, from having talked to a lot of people who use graph database management systems. A lot of the applications that graph database management systems are very good at supporting, where they add value, is in essentially query heavy workload. So you're looking for something very complex that requires essentially maybe finding a path between one node and another node, or even like just going like 2-3 degrees of neighborhoods around nodes to see what they're connected to. Again, like classic examples are fraud. Is this a bank account? Suppose you get a financial transaction network you want to represent as a set of nodes and edges. There are account nodes, there are transfers between accounts, and you just want to know, is this node connected to the suspicious node from, take your country. The challenge is that the graphs, by their nature, one core property of the data that applications tend to use graph database for is that nodes are going to connect to many other nodes. So there's going to be many-to-many relationships. So if one of your accounts is transferring on average to 100 different accounts, and they transfer to 100 different accounts, to the amount of essentially part of the database that you need to explore and search just grows for each hop that you do, for each join that you do. And so that ends up requiring scanning and sort of processing large chunks of the database. So in that sense, it's read optimized, or these systems need to be read optimized or query optimized, versus systems that might just want to be very good at sort of updates. And you're taking lots of transactions, you want to update them. They're not really transactional. As any database management system, they need to support transactions because people will want atomicity and durability. They don't want to lose their data, but they're not supposed to offer a lot of value in that space. I think that's a mismatch. So as a design choice, many of them try to optimize for this query speed So our storage is columnar because that's the core. Well, I mean, that's a very well understood principle that columnar systems are much more scan friendly. They give you opportunities to scan less parts of the data if the queries ask for less parts of the data than row oriented systems. So which means that every property that we have on nodes, for example, an age property gets its own sort of set of disk blocks or file, if you will. So it's columnar as a core principle. And in terms of storing the edges and edge properties, relationship properties, it's still a columnar system. We adopt a disk-based version of the well-known, CSR format. That's a very common format to represent sort of graphs in both in memory, and we have a disk-based version of it. So that's also columnar. I mean, it's actually called columnar sparse row format. So it's a columnar system. You can really think of CSR as a compression of two sorted columns. I won't get into it, but it's another columnar format. And we have one choice that we made, which sometimes I question actually, but we made it because that's what we've done in GraphFlow too, is that we double index the edge properties. So which means that if you have a connection, suppose, account A has sent money to account B, and there's a property on that edge, maybe the amount of money that was sent is 500. That we store that 500 twice, one for one of the nodes, the source, if you will, one for the other node, so that that's a choice that we made, and I think it's especially good in a disk-based system. I mean, it increases your storage, but by a constant factor 2, and you can't do less than that. Mm-hmm. And if you need to essentially scan the incoming properties of a specific node, and in general, you should always optimize for these very simple queries because they're going to be always most common. Just like in any phenomena in the world, there's going to be a skew in terms of the complexity of the query and how frequently you're going to get it in an actual system. So for the very simple queries, pinpoint queries where you say, give me this node and all edges around it. And if you need to read incoming edges, then you want to locate them. Like essentially, this gives us a way that they're all stored in the same page. So that's why we double index it. We don't double index node properties. So node properties can't, if you can, but you'd have to replicate hundreds of times if a node is being touched by 100 other nodes. Yeah. So that's another thing. So we got CSR format, we got columnar format for node properties, CSR format for relationships and relationship properties. We got double indexing there. And
just on that for a second, why do you sometimes regret that decision?
Well, because it's why do I regret this? So there is alternative ways. Like, I mean, I could get a bit technical, but there is alternative ways that we could reduce the storage, I think.
Okay.
I don't want to say I regret it. I sometimes question it because we didn't very, very properly study how fast we could have been if we chose to have just like, and that's what's the alternative method. The alternative method is what a relational system would do. You'd have a relationship table, no particular order there, and everything is kind of stored. All of the edges are stored there, and all the properties are stored once. But you'd have an index that essentially you need to have this index. You need to have for which node, what are its edges. Okay, so that's not storing the property though, that's just storing the IDs of the neighbors. And maybe using that you could just store the IDs of the edges as well, and then do a full scan with some smart way of filtering so you don't scan the whole tables. So that's an alternative way that you could store only once, edge properties only once, and you could still maybe do fine. Actually in GraphFlow, which was an in-memory system, we didn't double index. We actually did a single index, but it was in memory, so we'd have some random reads, but because it's in memory, we didn't care too much. We never really tested that, so I was a bit more conservative when we said we're gonna do a move to, not just me, back in the day, my student who implemented GraphFlow storage also implemented the initial version of Kùzu storage. We had this intuition that, let's just double index, let's forget about this problem. But we never properly studied this. That's why I say I sometimes still question it that, could we just store it once and still be okay? We never did that study,
One for an interesting research paper in the future, right, I guess.
Yeah, maybe. Yeah. So that's storage. So let me just tell you just very quickly about other things. So the join optimizer is a core sort of optimizer in every system where you spend a lot of time. It's a dynamic programming based optimizer, and Thomas Neumann really has done most work in that space. So we try to get that. We have a buffer manager that's based on another right now University of Munich based paper. VM cache is the paper. So it's that area is led by Victor Leys. He was at a different university and moved to University of Munich, where Thomas Neumann is. Yeah. By the way, for any of the listeners, Thomas Neumann is like the god in systems, in databases. That's why his name is coming up a lot. I mean, not only one god, one of the gods. And we do look at his work. And Victor is also at University of Munich, and he's done most work and the best of the work, I think, in buffer management. So we read that paper and try to integrate it into Kùzu. So we have a buffer manager based on VM cache. Let me not get into it. But people can easily find that, and we have a transaction manager. So that's very. I think if one day a historian went and said what was the simplest and correct transaction manager, I'm very confident it's correct, but it's also very simple. It's serializable kind of by design. I'm not super proud of it, but we had to add these features in the simplest way possible. I'm not proud of the way we implemented it, but I'm proud of the way of how simple we were able to implement it. It's based on write-ahead logging. So writes go into different sort of pages first, and they're logged, and during checkpointing they're sort of copied over, and by design you can only have a single writer in the system, so it's kind of optimized for bulk writes instead of sort of many concurrent writes. And reads and the write transaction, single write transaction, can work concurrently. So it is serializable in that sense. So maybe one day we're gonna sort of make that more optimal if there's any demand. But it's again, these are choices that we made. Our engineering efforts are based on optimizing the reads and scalability instead of transactions. So transactions, in one sense it's a bit naive and simple. It's correct, I think. It's relatively well tested, but it's also, we did a lot of simplifying sort of assumptions, like that we only allow a single writer in the system and things like that. Yeah.
Cool. So let's dig into a little bit more about the factorized query process, because this was the focus of the cider paper, right? So
that's right.
We've been through what factorization is, but maybe you can kind of touch on the design principles that you use when designing these new join operators. And I guess just tell us more about the ones that you've got in Kùzu.
Yeah. So factorization is, again, it's a compression technique, but it's not a compression technique you use to essentially make your disk files smaller, which is how compression is usually used on systems. You've got a file that stores maybe a property or a column of a table, and you want to make it short because you want to make it small because there's lots of repetitions and whatnot. Factorization is interesting because it's actually a technique that's designed specifically for query processing, for when the queries contain many-to-many joins, meaning that they can grow. So the core idea is very simple. So think of like the simplest star query. You got a middle node B, you got one outgoing edge to a node A, you got another outgoing edge to C, and that's your query pattern. So this is essentially what you would write in the match clause. And you want to find essentially all incoming and outgoing neighbors of a particular node B. And suppose you get a filter on B. And suppose that filter says, Jack's essentially outgoing transactions and incoming transactions. Give me Jack's neighborhood, basically. So that's the simplest essentially star query you could get. Now, if you've got essentially 10,000 outgoing neighbors and 10,000 incoming neighbors, now if you represent this output in flat format, it's 10,000 times 10,000. So, I think it's 100 million essentially tuples would be represented there. But there's actually the neighborhood is actually much smaller. There's only 20,000 edges there. So factorization is a way of representing this output as a Cartesian product instead. So it's Jack's, nodes, and data, Cartesian product with 1,000 outgoing neighbors, 10,000 outgoing neighbors, Cartesian product with 10,000 incoming neighbors. So that Cartesian product is another way to represent exactly the same 100 million tuples. And it's essentially, that's the way factorization works, that whenever possible, we try to essentially represent tuples, sets of tuples as Cartesian products in a much more compressed way, and pass that between operators. So you asked about the design goals. So one thing was just be able to implement factorization. And we had a particular way of implementing this based on my PhD student Amin's work in GraphFlow. It was really directly implemented in Kùzu. So we knew we wanted to essentially represent intermediate relations, not as a set of flat tuples, like maybe DuckDB does, or pretty much any of the other systems do, but in a factorized way. We also wanted to make sure we don't use index nested loop joins. So this is the type of operators that we in GraphFlow had, or Neo4j has. For example, an expand node, which is a join operator that takes a node record and expands it to its neighbors, for example. So if you use that in an in-memory system, maybe that's fine. But in a disk system, if that's the type of joins that you do, that is that there's an expand operator that takes a set of tuples, and for each one it expands it. So that's what in database literature is the way index nested loop join operators would work. So from one side you read the tuples, from the other side you go and scan and perform the join one tuple at a time, so for each join. So that's actually not going to be robust. I mean, I don't say that's always bad. Actually, in the paper there's many cases where that actually works the best in very basic cases, like you want one node and you want its neighbors. Expand type of join operators do well, but it's not robust when you are getting thousands, tens of thousands, hundreds of thousands tuples, and you need to do that. It just degrades very quickly because it leads to again you can't really localize neighborhoods, so it degrades to random IOs. So we didn't want to do that. So we wanted everything to be based on hash joins, which is the common kind of wisdom nowadays for doing joins, at least equality joins in systems. And we also wanted to make sure we don't, when possible, behave like index nested loop join. Index nested loop join has this one advantage, that if all I want is Jack's outgoing neighbors, an expand operator that just goes and takes the, maybe it was preceded by a scan operator that gave Jack's node ID. And all it does is that, just looks up in an index the IDs of the neighbors, and then does the minimum amount of IO and maybe read only the properties of those nodes or edges. So that's actually, good, because if you got, a 10 gigabyte file, you might just end up reading, I don't know, a few kilobytes of things. Even though it's random IO, you're just reading very few parts of the database. So in those cases, index nested loop join has an advantage. Again, I don't think it's robust, but we also wanted to behave like that when the queries were very selective, when we needed to join a single nugget or a single node record or a few node records. So those were the three goals: factorization, make it hash join based, but also try to avoid scanning all essentially files. And the reason this is a problem is that hash join always reads entire files. So by default, there's a build phase and there's a probe phase. There's no mechanism to say only read me the neighbors of this one particular node. So those were the three design goals, and we have a way of implementing this in the system.
Awesome.
With these specialized join operators.
Cool. Yeah. So maybe you can tell us a little bit more about these specialized join operators. So these three are in the paper. Maybe you can just give us the intuition behind how they work, essentially.
Yeah. So so let me just tell you the core sort of idea of how, in a case where you are maybe just reading Jack's neighbors, how this would work, and we would still be hash join based, but essentially achieve all the three goals. So it will be difficult to see how we get factorization because the query is too simple. So maybe let's just we could expand it to see how factorization is achieved. But suppose the only query, all we have to do is read Jack's neighbors. So what will happen is that, just like in any hash join, there's a build phase, which creates a hash table, and then there's going to be a probe phase, which essentially scans the left side of the hash join operator, and then does probes into this hash table that was built. So we'll do something along the lines of, you're going to read Jack's record, and we will figure out Jack's node ID. So maybe it's like 7. Okay, and then we're going to have a hash table that put 7 and Jack there. Okay, suppose you read only the name of Jack, maybe that's the primary key, but the internal node ID is 7. Now, all we need to know in the hash join is going to join that record with all of its neighbors. All we need at that point, once we create the hash table, we know that all that we need to scan are edges whose sources are 7. So we pass that, we do sideways, it's called sideways information passing. So we pass that information as a mask of node IDs to the left side probe side. And that probe side is going to essentially use that use that mask to know which parts of those CSRs to read. So it will only read 7's outgoing neighbors and avoid reading the entire essentially this file. And so we'll only get a way of we have this mechanism so that only 7's outgoing neighbors will be read, and then they will be probed and joined with 7. So that's essentially the core idea of how we avoid scans, is that we pass these node masks to know which parts of these either relationship tables or relationship sort of indices should be read, or some node properties should be read. So that's the core principle in these different operators. And so the way, how do we get so that doesn't explain how we get factorization. The way we get factorization is that, so in CSR, in the edges are localized, so we don't essentially pass that as essentially a sequence of, suppose you had 100 outgoing neighbors, we don't pass that one by one, we pass that as a sequence of 100 nodes with 7. So we just represent this as 7 times those 100. So that's the tuple that's being sent, and we're going to probe on 7. So that 7 and 100 outgoing neighbors will be joined as a single probe, not 100 probes. And with a single probe, we're going to read the Jack property, which was in the hash table. So that's the way, essentially, what's being passed is always these Cartesian products, unless some operator needs to essentially flatten and essentially break those Cartesian products.
Okay, nice. So I guess the kind of question that falls out then is kind of how much better are these join operators then on a graph workload? So maybe you could tell us a few kind of numbers, some of the experiments you ran.
So we did several experiments, and I'm not a big fan of system-to-system comparisons because it's very difficult to get these quote-unquote competitor systems in their ideal performing sort of configurations.
Yeah.
So we do try to compare essentially what an index-nested loop join configuration of Kùzu would look like with this, node mask-based Kùzu. So one thing that we want to do is, so we're isolating, we're just trying to study the pros and cons of this passing of masks, which is an overhead, basically, that's not something that index-nested loop join or hash join does, versus the benefits we get from essentially getting rid of index-nested loop joins in the system. So that's just one meaningful comparison, is that Kùzu's current version versus Kùzu index-nested loop join, which is essentially where we added an index-nested loop join operator to the system, where we do the joins using these expand-like operators. And the general message of those experiments is that when nodes are very selective, this overhead obviously is not worth it. It's expand type of operators are going to be better performing at those very high extreme selectivity cases. A couple nodes are being passed, but it degrades very quickly compared to essentially this node mask based operators. So we tested both on some large benchmarks like LDBC, plus some micro benchmarks, which are actually my favorite experiments of all systems papers, are those micro benchmarks, because you can really focus on a particular behavior of the system. And then, when the selectivity is very high, there's also an overhead, right? So when the selectivity is very high, you're not really getting much benefit from those passing those masks, because those node masks are not selective. They're not helping you avoid scans. So at those two extremes, there is an overhead and you could do better. But overall, it doesn't degrade the way index-nested loop join operators degrade, or it's not way off like DuckDB is, for example, which doesn't have a node mask, just does hash joins. by forcing the system to scan all these large files. So in comparison, it's kind of like a trade-off that you do. So at those extreme cases, there are systems that would outperform this type of processing, or there are techniques. But overall, it's like, I think, a reasonable trade-off to make, that your system and your query processing is more robust. So that's the type of sort of evaluations that we provided in the paper.
Fantastic. Yeah, I recommend the listener goes and checks it out as well. But I guess on that, so I guess it's possible to kind of support both types of operators in the system, right, and have some sort of optimizer that lets you choose specific ones based on the selectivity or whatever, right? So I mean, you can get the best of both worlds in some
I agree. It's doable. Actually, one of like there's two first authors of the paper, Xiang and Godong. They contributed the most to the paper, so they're listed as first co-authors. They have been sort of arguing of when we should avoid semi-masks and this node. We call it semi-mask, but these node masks that I mentioned, when should we just avoid this overhead completely? Because it's like, if we kind of during runtime see that these node masks are not being selective, we might maybe avoid it and do something adaptive. Or if you're smart enough, your optimizer is smart enough to predict that node mask will not be selective, you could just remove it and replace some of those join operators with index loop join. I agree. It's a question of like, it's always an engineering question of like, do you want to invest that time, like, or are you happy with how your sort of query processor is performing, even with those overheads? So it's a matter of that. But I do agree that and in our experiments make it visible that there is performance that we put on the table, and it's like that our trade-off is there explicit.
Awesome stuff. Yeah, but I'm going to kind of roll the next two questions into one, because I always ask kind of what are the limitations of whoever I'm interviewing, whatever they're working on. But obviously, Kùzu is a very young system, so I mean, a lot of it's not feature complete, right? So I mean, there's a lot of road to run still. So I kind of want to ask you more like, where do you go next with Kùzu?
Yeah, so I have several sort of theses that are being written on Kùzu. One thing that we don't do, or we haven't sort of invested much time in GraphFlow 2, there was no work on this. I didn't have a student to take this topic. Is recursive queries, so which is essentially actually an area that graph databases need to shine in. Certainly their query languages are much better for recursive queries, because recursive is kind of a first-class citizen historically too. Like even in those systems in the 60s, 80s, 90s, 2000s, in all those graph-based systems like RDF, object-oriented system, even like the 60s system like IDS, recursive applications that wanted to do recursive querying were always some of the killer apps. So there is a thesis being written on that. So we are essentially trying to implement some new query processing techniques for like shortest paths, or for variable length joins and things like that. A second thing that I'm very interested in, and I have a student who's going to start working on this, and we have some ideas, is how to make property graph database management systems more competent on RDF style graph data. So that's another sort of popular data model that people broadly label as graph based. And I do think, the property graph model, so this is like a position that I try to articulate. So I think out of all the graph-based systems, graph-based models, property graph model is the most generic one, in which you could build the most sort of applications. It's more generally applicable, just like relational model as a model is very generically applicable. So RDF, I don't think is RDF is a very specific application domain. I'm not saying it's a small application domain, but it's really suitable for a specific sort of application domain as a model. But property graphs are not. Property graphs are just as relational model is very generic, is quite generic. You could represent lots of application data. And actually, this is one of the other things that we mentioned in our survey paper back in 2017, that when we asked people what kind of applications they built on these things, people just told us just all types of things. So, and they could, I think, with some specialized techniques also efficiently support RDF style knowledge management and some techniques to maybe do some OWL-based reasoning and those things. So I don't think vice versa is possible. So I don't think you are going to manage your transactions with RDF systems or like financial transactions and frauds. I don't think that's a very good fit as a model. But I think, property graph based as a model is a good fit. So I will, there will be a thesis written on how to essentially make property graph based systems, and specifically this will be done obviously on Kùzu, more essentially techniques to make the system more efficient in RDF style knowledge management, and maybe some level of reasoning. Very related to that is a topic that's gonna sound very boring to people, but I still don't know what's the right way to manage strings. We don't know this. There's actually no authoritative paper in the field on this. There's some authoritative there's some state-of-the-art compression techniques, but there's no authoritative paper that makes an advice. If you assume this thing about your data set, here's maybe the properties of the strings, their length, etc. And here's the right way to sort of store it on disk. Here's the right way to store, manage the overflows maybe of those strings, or because that's a variable length data type. And here's the right way to represent it in memory. So we do these things where we kind of sometimes blindly copy from Umbra or DuckDB these things, but I don't think it's very well understood. I have this dream of finding a student to actually just do this investigation for about 2 years to sort of do this experimental study of here is all the techniques that's in the field of how to store things in memory, how to strings in memory, how to manage them in memory, how to process them in memory, how to store them on disk. I don't know if they'll get a chance to do that, but that's something I hope I can find a student to do on Kùzu as well.
Yeah, it's one of those things. On the face of it sounds quite a hard sell, but I imagine that when you get into it, it's fascinating, really interesting project once you kind of got going with it. So hopefully a listener listening to this now thinks, okay, I'm going to go work on strings for 2 years. Yeah.
Maybe. Yeah, but I mean, so Hannes, who is the CEO of DuckDB Labs and one of the main engineers there, also mentioned this actually in his keynote at Cider this year, where Kùzu paper got published. He said he's very surprised that few people work on strings, despite the fact that majority of the databases are strings. And there needs to be one authoritative paper, I think, that makes this advice. This is how you should implement strings if this is your assumptions. And I want to see that chart of whatever those assumptions are, maybe some workload assumptions, maybe some, data set assumptions, and then says, here's a good thing that we found that's robust and easy to implement and whatnot. Yeah.
That would be a really good contribution. I get, so the next sort of set of questions I have, I tend to sort of ask them to everyone with very different flavors. But the first one is how as a software engineer or data engineer can I kind of leverage your work? But I guess the answer to that is just kind of go and play with Kùzu, right, and try and integrate it into your workflow and see if you can kind of fit it in. So I guess the follow-up question to that would be longer term, what sort of impact do you think Kùzu can have?
So let me also just maybe on the previous question, I wanted to say those, I just kind of focused on the research things that are happening. There's also, as you said, Kùzu is a young system. So there's a lot of engineering that's happening to add a lot of features. And we're getting excited about sort of making Kùzu more usable in the graph learning space and trying to connect more with users. So we are adding some features specific to these graph learning libraries. So there's going to be all those integrations that are happening. So for that question, so I think playing around with Kùzu is probably the right message for developers or general application developers. I mean, if you're a developer of graph database management systems, you're in Neo4j. So for people, engineers of Neo4j, I think there's some core messages that we think some of these core join techniques should get into these systems, and there's a lot to benefit. For other application developers, I think there's a set of application domains where really relational model and SQL is not going to be a great fit, nor are the systems that implement SQL are implementing the right sort of techniques to be very performant. Even the most state-of-the-art techniques like Umbra, is not going to be really, really well in many-to-many joins, for example, or very, very well in recursive joins. Like recursion is something that's always a second thought in relational systems. It's a first class in graph systems. So, if you got applications that benefit from these set of features, and there's more in my blog post, I think I've listed about 5-6 of these application domains. I think just being sort of knowledgeable about this alternative database management systems is going to make them better engineers. So because like trying to retrofit every application to relational model is, I think, not a very good idea. So people should be educated more on graph database management systems and these alternative database management systems, their models, their query languages. So it's going to make them, I think, better engineers.
Yeah, for sure. Yeah, definitely agree. Yeah, my next question, I think you touched on this a little bit earlier on when you were talking about the journey and GraphFlow and whatnot. But I guess on this journey you've been on, what's probably the most interesting thing that you've kind of learned, and that was maybe quite unexpected as well?
Yeah, good question. This was the question that I thought most about. I don't have a great answer to this. I asked Xiang and Godong, the two authors, what were their what was the thing that they found most unexpected or interesting. I guess I think we learned a little bit more about ourselves. So we haven't done this before. So I am trying to do this in Canada. So, by following DuckDB or systems like Umbra or Hyper, this is a specific sort of research style that's quite popular in Europe. So both DuckDB and this Umbra Hyper type of systems are being developed in academic settings in Europe. And I'm trying to, my group is trying to replicate that in Canada with Kùzu. So, we are doing a lot of engineering and less sort of paper writing than maybe normally researchers in academic settings do. And we are doing this for the first time. So one thing that we are noticing about ourselves is that how this it's more a psychological thing that I'm finding interesting. How often we get wrong, how often our intuitions are wrong about what is important and what is not. It just becomes very difficult to judge these things in absence of a large user base. For example, let me give you an example. We did start the project and spent a lot of effort trying to implement this second storage structures in the system to store arbitrary key value properties. And, that just slowed us a lot, and that was a lot of code. And right before we released back in November, we said, you know what, let's just see if anybody is actually interested in this, or are people really structuring their graphs, and we're going to add this back on. But so that was when the project started, maybe a year and a half, 2 years before that, that was nobody ever questioned that we should not have started this. And the mistake that we do often, we're noticing that we're over optimizing. We get too sort of optimistic about, this is going to be really important, let's certainly do it, versus, and we kind of, we trade that off with simplicity, and we kind of implement more than we should, and we throw away. So that's a mistake we consistently do. I think we're getting it better, but that was something that, we started seeing more concretely by the amount of code that we're also throwing away from the system. Yeah. So that's something to keep in mind, that, that's a very important lesson, I think, that if we were to do this again, many of the features we just start much smaller and get it right, to get it complete and optimized and evolve. Just like text and writing papers, you write something. The best way to write, as they say, 12 pages is write 24 pages and throw half out. But,
yeah.
Start simple, add more, and optimize it. It's just going to evolve over time. Don't overdo it. Is one thing we've realized ourselves. It's a mistake we made.
But is the quote right? Was it premature optimization is the root of all evil, or something like that? Right?
Yeah, maybe something like that. Yeah. So
like that, right? Yeah,
it's very real. Yeah, we've done several of those for sure.
Cool. I guess kind of while we're talking about the journey as well. What were the things kind of along the way? Maybe this is probably an example of that. But you tried that end up failing that you think might be interesting people to know about. But maybe this is a good example of that anyway.
So I could tell you sort of ideas we didn't take from GraphFlow, because we were able to write sort of good papers on them, but I don't in the end advise people to implement them. So for example, we have this paper on A+ indices. It's a way of bringing materialized views into graph database management systems. I think they're a fine idea, and we published this in ICDE, which is a top conference and whatnot. It's a good interpretation of how materialized views could be brought into a system as these indices that support essentially subsets of your edges, which are effectively results of some queries you may have run on the edges. And we found sort of fine applications of it, but it's also now very practical in the sense that it's a lot of effort. And that when we sit down and we say, okay, we got a budget of this much engineering we can afford, should we do the A+ indices, or should we do, like, it was like clearly one of the things we said, no, we don't have to do this. It's not really worth it. So in some sense, if you want to interpret it, it's a failure in that sense, because it doesn't offer something very practical, I think. The amount of effort is something we can't afford right now. So there are ideas like that we brought in, and there was a lot more work on factorization that we did that's in Amin's thesis that we are not adopting, because again, I find it's good to do research projects, because without those courageous PhD students doing those research, you can't really distill the practical ideas, I think. But I don't think we really got it right yet. So if you looked at the theory of factorization, there is excellent ideas there. Like so the form of factorization that we do, again, this is for interested students who might look at this, is called F representations. There's another more even compressed versions that you could keep called D representations. It basically stands for factorized representations with denotations. The D comes from the denotation. And we don't have a way to essentially adopt that. Again, Amin has something in his thesis, but again, I'm not courageous enough to actually say, because the way Kùzu is trying to be is like to be a very practical system. So I'm very selective on what gets in and what doesn't get in. But I think it's good work that Amin has done. But I'm saying that there needs to be more work until we actually feel confident that, okay, the representations can now be integrated into the system. Yeah. So I don't know if I answered your question, but there are tons of failures. That's in the very nature of research. I think that a lot of the ideas, I think we just get wrong. We publish them, and then somebody else does something better, I think, and then hopefully some core sort of principles emerge that we know how to do that in a more practical way.
Yeah. Out of interest, how big is the team at the minute that's working on Kùzu? How many engineers?
So there's, I think, 5 of us, including myself, and 3 master students. So the 5 out of the 5, many of them are doing mainly engineering. They're in the university and whatnot, but they're really less, because they got their degrees. So they're staying as research associates. So they're less, or they're postdocs. So they're less worried about, and they're really trying to. They're less worried about publications, and they're just very inspired by sort of trying to be like DuckDB and get a user base. So they're doing more engineering, although, obviously we are going to continue writing papers, and then there's a couple people who are new, whom I've started training recently, and they'll write some of these theses that I mentioned over the next 2-3 years. So, but like, however you count it, including me, maybe 7-8 people are. Some are very junior and not doing any engineering, just research, and some are like doing more research.
Yeah. Is Kùzu kind of your whole sort of like vehicle for research, or do you have other sort of non-Kùzu related projects going as well?
Yeah, so we recently published a paper. Actually, Chang, who is also an author on Kùzu, it was Chang's master's thesis. Chang kind of was doing a project on open government data sets. That was a research project that I'm actually very excited about as well. So this is an area, I would say, led by René Miller. One of the main people in the space is René Miller, has a long history of research in open government data sets. So these are the data sets like, UK has one, US has one, data.gov, Canada has one, opencanada.ca. These are ways governments are publishing essentially lots of data sets about how the government runs, with the goal, long-term goal of transparency, more essentially democratic access to how essentially the governmental institutions are running, for journalists to keep an eye on sort of some maybe, I don't know, inefficiencies and major problems in the society. And it's now very usable though, these data sets. A lot of the people, it's now very easy to find them. It's now very easy to integrate them. So I have a research project. It's unfortunately gotten a bit smaller since Chunk decided he'd rather work on Kùzu, to essentially make these data sets more usable. So I still have, actually, I'm currently this week writing a paper on that. So I have that going on, and I have a PhD student who's graduating also this year who has been doing work on differential data flow and applications of differential data flow to graph processing. So for those of you who may not know what differential data flow is, differential data flow is one of the technologies behind Materialize Inc. It's a popular startup in the data space. They do essentially streaming SQL and to materialize your queries, although I might be wrong, so check what they do. But they're basically using a technology called timely data flow and differential data flow, which Frank McSherry was very influential in popularizing. So differential data flow is the most generic incremental view maintenance technique that I'm aware of. It can maintain arbitrary data flows. And one of their best applications is on recursive, essentially, data flows and how to maintain the outputs of recursive flows. And it relates directly to graphs because a lot of sort of graph analytics is recursive computations. Like if you want to find shortest paths, if you want to find connected components, those types of graph analytics is often represented as recursive queries. And if you represent that recursive essentially computation as a data flow and give it to this differential data flow, and your input, your graph is changing, it's going to maintain your connected components, or it's going to maintain your shortest paths, which is an amazing technology. It's actually unique in the sense I don't think there is another technology that's able to do this. So he has been, my PhD student Siddhartha has been working on building essentially graph layers over differential data flow. So I have that going on the side. Although again, these have gotten smaller because the students are leaving to either move on to other things or to move to Kùzu and things like that. Yeah.
Great. So yeah, I've got 3 more questions. So the first one is I like to ask people listening. It's really interesting to see the divergence in answers I get for it. So and I'm sure you'll have a totally new perspective on it as well. So it's like, how do you go about approaching idea generation and then determining what to work on? I'd love to know more about your creative process.
I see. So it's a very difficult to answer question. So some of these are student driven, obviously, at this point. And back in the day, it was a bit advisor driven. So back in my PhD, it was a bit advisor driven. So a lot of the very productive work that I did actually back in PhD came from Jeff Allman. Jeff is a Turing Award winner for all those. I'm sure people have read Jeff's books. So Jeff I did a lot of work with Jeff during PhD, some theoretical work. And they were really driven by Jeff and Foto Afrati back then. She was a collaborator of Jeff. So back then it was driven by that, and they would give me specific problems. They would be very well defined, and I'd work on that. So that was the style. Now some of the problems are also reverse, where some students are gonna bring ideas. But so often I work the way I work nowadays is I start with very, very naive, simple things. I make sure that the most naive versions of things get implemented. So I'll pose a problem like, how should shortest paths be implemented, which is an ongoing project right now. What can we do in that space? And the first thing that we're going to do is we will do the most basic ways of implementing this. And frankly, most of my best ideas come when I implement those things, or I see my students implement those things and I look at the queries. I find it difficult to come up with very good systems research ideas I can come up with high level directions, but then in the end, I can't often predict what the papers are going to be about beforehand. And that comes only when we implement something. And then we see, okay, these are the challenges in the implementation. So I highly advise all of my students right now, and this is the sort of style that I've come to adopt in the last 3-4 years. It's extremely sort of code driven. Everybody needs to write a lot of code. I think that's good for training as well. And everybody needs to work in the context of a system. So one thing that I'm very against is publishing ideas that are not implemented in serious systems, because they're kind of destined to be, I think, out of touch with the reality of how things get integrated into a system, which means they're going to be dismissed. So everything needs to be implemented in a serious system. Like Kùzu at this point is becoming quite serious, that if you do research on Kùzu, you will get to interact with a lot of components of the system, or you need to take, like I'm advising a PhD student, not really advising, but I'm talking to a PhD student who works on Neo4j at University of Waterloo, and she does work inside Neo4j, which is good. I mean, that's the style of, I think, research should be done. And when you do that, I think, do you get good practical ideas. Now, that has one risk, which is that when you do that, your ideas are also more humble, because you're kind of highly limited by what can be done, versus if you were to kind of feel freer and do something on the side on your own scratch code. So those papers are more easily rejected. So I do get a lot of rejections. My students and I know a lot of the work that we do gets quite a bit of rejection, unfortunately, because some of the ideas end up more like, here are some sort of core engineering principle, but they don't, it looks a bit, it's a bit hard to make them look fancy from a research perspective. But that's a style that I work, I think. Yeah. So write the code and see what doesn't work. And then after enough failures, good ideas come, I think. And they always come, by the way. So
yeah,
no need to worry about that. Some idea always comes on that you can publish, I think.
Awesome. Yeah, that's another great answer to add to my collection of answers for that question. Great stuff. Cool. So just two more questions now. So the first one is, what do you think is the biggest challenge facing us now in database research? Maybe specifically, we can focus this towards like graph data management. And there was a recent debate on graph database published in the Register. I'd like to get your take on that as well, if possible.
Actually, I didn't read them because I find those things a bit distracting. So some of those are more around personalities than I think, or some companies have essentially energies around them. So I genuinely did not read them, although I know the general topic that was discussed, and I obviously have my position. So like anybody I think who claims graph databases will take over relational systems is way off in their predictions. I don't think that will happen. I think we gotta be, the relational market is humongous and very well established, and I don't think people are gonna switch to graph technology for tons of applications that they will. So that's not gonna happen. But anybody who also says graph databases are going away are, I think, way off as well. I don't think they're going. And actually, as I have tried to say, this style, the one that Neo4j kind of brought, the data model and the Cypher-like sort of query languages are going to stay. And I think they're actually they're likely to be the most successful of every wave that has come so far. And there's more buzz around them too, but I don't see them going away like XML databases. That I think they're here to stay. I think they've got a relatively healthy sort of application base, and more can be done in the graph state. One reason that convinces me of this is that there's really no other data model other than a graph and tables that is very generic to represent application data, and there will always be appeals to choose one over the other. And some of this is also just sociological question that people just prefer thinking of certain sort of records as nodes and versus tables. So they've done a good job. I think property graph model is a good model. So I do see it remaining for around. So that's also way off. But obviously, I don't think graph databases are going to take over relation systems or something. That's just that's also way off. I think that doesn't demonstrate, I think, a good understanding of the core sort of power around relational systems. But graph databases are here. They're going to get better. The market is going to grow healthily. I think there will always be many applications that use those systems. What is a challenge in databases? I don't see myself as a visionary, frankly. So I can't sort of foresee what kind of big problems people are going to work on. But one thing that I am kind of inspired about. Like this, I'm just putting it out there so that maybe some PhD students who might run into this podcast might want to get curious about, is there has been an ideal way back, actually stemmed from AI, artificial intelligence, from very early days, historically, of building information systems that can do deductions. And that has its own niche sort of communities with like automatic proofs and things like that, where it connected very well with the database community back in the day. I don't think the communities talk as much, but these logic-based systems like Datalog is essentially a part of first-order logic that really captures the relational calculus. But it's a very limited part of first-order logic, and the logic-based sort of AI community, the symbolic AI community, has done a lot of work on finding essentially algorithms that can do deduction. So let me give you an example. Actually, this is an example. I wrote a blog post on this that will appear at Sigmod Records, but I think 6 months from now, for some reason, they said it would appear in Sigmod. But here's an example that if you read a book on those sort of core AI topics of knowledge representation and sort of applications of first order logic to essentially knowledge representation and deductions and whatnot. So one example that they will give is think of a database, a table of essentially items, some elements, maybe some balls, and they have colors. So maybe the colors are red or black. And then there are some nulls. There's some balls whose colors are not known, but there's a constraint that says that every ball has, which you can do in first order logic, which you can do in some logic-based systems as well, database systems, I think as well, that there's a constraint that every ball has to be blue or black, right? So with relational algebra, and my question is that what is the maximum number? What's the color of the balls? What's the maximum number of reds or blacks? Okay, so out of all buckets that you could have in terms of colors, what's the maximum number? And suppose again there's 3 records, one is blue, one is red, one is null, but there is a constraint that colors are either blue or black. Now the answer is 2, but no relational system can compute this, right? Because no relational system is going to be like, you can't, like, you need some other algorithms to do this deduction and use the constraint and be smart that the maximum has to be, like, you need to do a little bit of a proof there, right? You need to say that, okay, there's 2 cases, either this null is red or this null is black. Let's do the query. When it's red, you get number 2, because now there are 2 reds. Now, if it's black, you get 2 as well. So the maximum has to be 2. So that's the correct answer. And obviously humans, we can answer this very quickly, but no information system right now, no database system will do this, because we're really restricted to very small part of first order logic. I think a good thing to think nowadays is to see what, like, first of all, I don't even know how well motivated it is with this current AI sort of applications, but it's an ideal. I think that's important to remember as people think about reasoning, as people think about sort of what can we do to extend AI applications with some logic-based deductions, because people are talking about neuro-symbolic AI. And I don't fully understand, again, the applications to see if this sort of gut feeling that I have that this might be a good topic to look at is important. But at least as an ideal, it has existed for over 50 years maybe, of how can we build more intelligent database management systems by extending the part of sort of first order logic that we capture. So, if somebody does the work of seeing if there are applications of this, that more deductions could be good for certain applications, I think it's a good time to start. And maybe 10 years from now, those systems might be really useful, because this logic community has done a lot of work to find a lot of algorithms, and it's the right time to think about how many of those can actually be put back into a database management system, make practical and whatnot. So, that's an area that I think is important. Then there is some classic areas like nowadays heterogeneous computing, GPUs, DPUs. How do we bring those kind of hardware into database techniques? Those are clearly very timely to do, I think, to write PhD thesis on too. So yeah, those 2 immediately come to my mind about if I were to be a PhD student now, I'd explore those type of things and it's as usual as every decade. It's very exciting. There's tons of things to work on.
Yeah, well, there you go, listener. You've been told those are the things you need to go work on.
Well, I see. Yeah, maybe.
Yeah.
It's at least good to explore. I think it's
Yeah,
good to explore.
definitely. So really
Yeah.
interesting directions. They're cool. So it's time for the last word now. So, what's the one thing you want the listener to take away from your work on Kùzu and from this podcast today?
So I'd like them to first of all understand that Kùzu is being developed seriously. So I'd like to see more people use Kùzu. We got our sort of first set of users who are trying and playing around with the system, which is exciting to see. But it is a system that aims to be highly scalable and sort of fast on graph queries. These join heavy queries when you need to find connections between nodes, and it is adopting the usability style of DuckDB. So you can think of it in one sentence as DuckDB for graphs. So that's one thing to take away. And that's about Kùzu. Did you want me to comment about something else?
That's if you wanted to.
And the other thing is, I do think educating yourself a bit more on other data models is going to help you. Knowing more about RDF, knowing more about property graph database management system in general is healthy. And I think, for anybody who's teaching courses on database management systems, I think I do this all the time. Spend a couple lectures on these things. I think we need to educate people more on these alternative models that go beyond the alternative data models and sort of variants of SQL like Cypher and Sparkle, and those languages they're easy to pick up, and it's good to know because you want to be able to use your skills on those technologies easily. I think it's going to make people better engineers. So that's another thing that I want to advocate very, very strongly for.
Fantastic. Well, that's a great thing to end it on. So, yeah, we'll end it there. Thanks so much, Semih. It's been an absolute pleasure talking to you. Thank you so much for coming on the show. If the listener is interested in knowing more about all of Semih's work in Kùzu, we'll put all the links to everything and all the blog posts and whatnot in the show notes. And if you enjoy the show, please consider supporting the podcast through Buy Me a Coffee. And we will see you all next time for some more awesome computer science research.